Hey CTMers, welcome to the lesson for 14.2, continuing our discussion on graph theory as we continue through this chapter here. In this lesson we're going to be talking about Euler paths, Euler circuits, Euler's theorem, what an algorithm is, and then Fleury's, I'm a little shaky on the pronunciation there. This is definitely Euler though, so not Euler but Euler, and Fleury's algorithm, and what that looks like and how that pertains to what we're talking about here. So as always, make sure you're using those extra examples in your book. There are 6 extra examples in the book listed for this one. We're going to do 3 together here. So you've got a total of 9 examples. That's some good math right there, Mr. Wagner. Thanks. 3 plus 6, that'd be 9. That's nice. Okay, let's get started. So this guy, if you remember this guy, he comes from, we talked about him way back when in chapter 3. And 3.6 to be more specific, we talked about Euler diagrams and how that related to logic and logical statements. But now we're talking about how he has influenced not only that branch of mathematics but also a lot of others, including graph theory here. He was foundational in his work in graph theory, kind of laid the foundation for the rest of graph theory. So we talked about that Königsberg bridge problem. We're going to refer back to that here. But let's get some definitions down first. So we talked about paths, and we talked about circuits already. Now we're going to talk about something called an Euler path and an Euler circuit, and how those are different from just a plain old path and a plain old circuit. So an Euler path, it's still a path as we defined it before. So it's a connection of vertices going through different edges, put it in layman's terms sort of there. But it's a path that passes through each edge of a graph exactly one time. So each edge gets crossed to pass through exactly once. In an Euler circuit, it's just like an Euler path, except instead of a path, it's more specific. It's a circuit instead. So an Euler circuit, I'm still getting over that sickness or that sore throat that I had. Hopefully you'll be able to hear me okay and my voice won't give out and whatnot. So it's a circuit. A circuit, just as a reminder, what is a circuit again? It's something that is starting, so that is to say it starts and ends at the same vertex. So in other words, it's a path that starts and ends at the same vertex. That's a circuit. And then an Euler circuit is one that passes through, so it's the same idea here, it passes through each edge exactly one time. Excuse me. And then at this point, I just want you to listen to this part here. So I'm going to draw some pictures in here, and then we're going to talk about those pictures. If you really want to draw them in your notes, you can, but you can just listen at this point. So here are 3 different graphs. Again, you do not have to write this part down. I more or less just want you to listen, unless you're just adamant that you have these examples or these as examples down on your paper. So I just want you to listen at this point. And we're going to try to see if there's an Euler path or an Euler circuit with each one of these. And so I'm going to use my different color here to start tracing some things and to see what we have as we go. So once I pick a point, I can't pick my pen off the paper. I just need to keep going from there. Why don't I use, that'll be kind of cool. I'll use my highlighter tool instead. And so go a little bit smaller. There we go. Yep. Ooh, yeah, I like that. Alright, so let's just say I start at A. Let's see if there's an Euler path or an Euler circuit I could do. I'm going to try to draw a circuit if I can. So I'm going to start at this point. I'm going to start going along the path that I'm picking here. And so now I have a choice. I could go towards C, I could go towards E or I could go towards D. I can't go back to A though because I've already covered that edge, and I can only cover each edge exactly once. So going back over that wouldn't work. That's no good because that would be going over an edge twice. And so let's say I did that. Now I could go here. I'm just going to make a decision. Now I could go here. That's the only way I could go from that point. And then from there, it looks like I could take some different options. It looks like I could go this way, and then this way, this way. It's okay to touch a vertex more than once, but just not to cross over that edge again. So here, here, and here. So this one, it looks like we were good to go there. This one, it's possible to make an Euler circuit. And so again, you don't have to write this down, but this one, Euler circuit. And I happen to notice here that there were 2 edges here, there were 4 here, 2 here. Each one of these vertices happens to be an even vertex, has an even number of edges emanating from it. And so here there are, in other words, no odd vertices. Interesting. Okay. So Euler noticed that as well. This was an Euler circuit. It was possible to draw an Euler circuit here. If I take a look at the next one, let's see what I got. So let's say I don't want my paint tool. There we go. Highlighter tool. Let's say I started at A and I started going along. So I go here. Okay, I've got a choice. I could either go towards D or towards E, but it looks like either way I go, if I went towards D, then I couldn't get back to the B and A part if I went down here, but I couldn't get back to the bottom part if I went the other way. So that didn't work. And if I went this way instead, I'm going to get stuck right here. I can't go back over that edge. So that didn't work. So I noticed, I started at an even edge right here, or an even vertex right here. Let's try starting at an odd one instead. So let's go here. I'll try going down to there. That would be my only option. Then I would have to go this way. From there I've got some choices. Why don't I just go up this way, and then I have to go here, I have to go here, and then I would have to go here. So notice that I have drawn an Euler path here, but not an Euler circuit. So with these kinds, notice how many odd vertices you have. You've got 1, you've got 2. These both have 3 coming out of it, 3 coming out of it here. The rest are even. And so on this one, notice that you have exactly 2. There's 2 odd vertices. And then on this one, well, let's see. We're just making some hypotheses here. I notice this one has 4, so that one's even, but the rest of these have 3. They're all odd. So I noticed it wasn't good before when I started at an even one. But why don't I see and test that theory here, see if it still holds. So if I go here, here, well, I could go here, but then I'm going to have a problem because I can't get back to the arc AD. I can't do this part up here without crossing over an edge again. And so I could end up going here and here, but then I'm stuck right there. There's edges that I've already gone over, so that didn't seem to work. You could try that. If I started at one of the odd vertices instead, and I tried to loop around, let's see what happens. So I just make the whole circle there, but then when I go to here, excuse me, when I go to here, I'm stuck no matter which way I go. If I end up going this way, I have to cross over an edge again. This way, same thing, I have to cross over an edge I've already gone over again. So in this one is not possible. We didn't prove that was the case. The proof is beyond the scope of what we're doing here in this book, but neither is possible with that there. And so when does that happen? This is when you have more than 2 odd vertices. Okay, so that was a just listen part. If you want to write that down, it might be helpful. But if you wanted to leave that out, that is up to you. But let's now take what we've learned here, take what we've hypothesized here, and let's check out the theorem that goes along with it. So we're not going to prove that this is true. Again, that proof is beyond the scope of what we need to do or what we're going to do here in this book. But this is called Euler's theorem. I guess I could have centered that a little better, but that's okay. This would be part 1, part 2, and part 3 to Euler's theorem. It says, just like we saw here, if you had no odd vertices, I don't know why I'm leaving off the O there, no odd vertices, that would imply, or that would mean that you have at least one Euler circuit. So I would assume that Euler was the one that first proved this, since it's named after him. Most of the time that's what happens in math or science. If you prove something or name or discover something, you can name it after yourself or whatever you want to name it after. So this one, this is a little extra information about the theorem. You can actually start at any vertex with this. You can start at any vertex and end up get an Euler circuit. It's pretty cool. It always works out. No matter where you start, you can get an Euler circuit. Part 2 said if you had exactly 2 odd vertices, has to be exactly 2. That implies that you have at least one Euler path, but no Euler circuits. So not possible to draw an Euler circuit, but it is possible to draw at least one Euler path when that is the case. And with these ones, this is also the case too. So this is a little extra note that you must start, and we noticed this here when we did this quick example. We had to start at one of these odd vertices in order to get an Euler path. We couldn't start at one of the even ones. So you must start at, definitely write this down here, you must start at an odd vertex and end at the other odd vertex for an Euler path. And then number 3, if you have more than 2. So this one was exactly 2, this one was none, no odd vertices. More than 2 odd vertices. Sorry for the crazy, nasty, despicable, ugly, horrendous looking eye there, but this would mean, man, neither Euler paths nor Euler circuits exist. And so since there's nothing that exists there, there's really nothing extra to write underneath there. You can't get one, so you don't have to know where to start because it's not possible. So let's look at our first example now. This is going back to the Königsberg bridge problem. We're not going to redraw the map, we're just going to redraw the graph. So let's write that down here. Using the graph of the Königsberg bridge problem in our notes from example 1 in the previous lesson, lesson 14.1. So if I bring that up here, here's 14.1, the completed version of that. We had our problem here. This was our rough map that was equivalent to another way to draw that, where the land masses are still in the relative same area, and then this was the graph that we came up with. So I'm going to just copy and paste this graph, and you're just going to do the same sort of thing, but just make this graph. Once again, we're going to put that in our notes right over. Why don't we put that right over? Come on, I'm not letting go of my pen there. There we go. Over in this area. Okay, from there we're going to determine if an Euler path or Euler circuits exist. So let's see what we think. This will be our solution. SOLN standard for that. So we need to determine, first of all, how many odd vertices there are. That's the big thing. That's the key that we need to figure out. So this one has 1, 2, 3. As I go around in a circle around vertex A, I see 1, 2, 3 edges coming out of it. With B, I see 1, 2, 3, 4, 5 edges coming out of it. So I've got 2 odd vertices already. It's not looking good. If I find another odd vertex, we've got too many. So this is 1, 2, 3, another odd vertex, and the fourth one actually happens to be odd as well. So they're all odd vertices. You've got 4, which is more than 2. So we would say something like this. There are, excuse me, 4 odd vertices. So by part 3 of Euler's theorem, and a short way to write theorem, in case you forgot from geometry class, was THM. No Euler path exists, or Euler circuit, I should say before I say exists, or Euler circuits exist. So the people of Königsberg, they posed this problem, I would assume, to Euler and said, is this possible, Mr. Euler, Mr. Leonhard Euler? Could we start somewhere, walk across each bridge exactly once, and then excuse me. So sorry, I had to cough there a moment. Walk across each bridge exactly once, and then end up either back where we started with. That would be a circuit, or at very least not go over a bridge more than once. So you could do something like this, but then if you went across this bridge, you'd have to go over this bridge again to get to that bridge. So there's no way, we're not swimming across the water. Sorry, that doesn't work, that doesn't count. There's no way to do this without crossing over an edge. At least one edge, bridge in this case, is the edge more than one time. So we have that going on there. With that, so Euler's theorem, it proved that that was not possible. He actually proved beyond a shadow of a doubt that if it has more than 2 odd vertices, that the graph, you can't do that. You can't make an Euler path or an Euler circuit. Alright, so example 2, we're going to refer back to this problem now. I'm not going to have you redraw the outline of this. I'm just going to have you redraw the graph that we had done before. So using the graph in our notes, I told you before that we were expanding on, or we're going to talk a little bit more later about applications, or actually figuring things out about the problems we had drawn graphs for. We're doing that now. This is when that's happening. So in example 2 from our 14.1 notes, determine whether it is possible to cross each common state border exactly one time, and if so, give a possible path. So it's not saying that I have to start and end at the same spots. That would be a circuit. It's just saying that I have to cross each common state border exactly once, so each edge gets crossed exactly once, in other words, and we're trying to give a possible path, if that is possible. So in our drawing before, we weren't counting Kentucky, West Virginia, Virginia, North Carolina, or South Carolina. We just had those states right there, those 7 states. So if I go back to my 14.1 notes, sorry, I get to cheat, and you don't. I'm going to just copy and paste what I see there into my drawing here. And this might be a little tricky here, because I think I'm going to be grabbing the word path. Yep, I'll have to bring that back. Go back, make the P again. There we go. And alright, this is going to move back this way. Exactly. There we are. And so draw that picture, pause if you need to recreate that picture on your notes here. And so let's think this through now. So what's our solution? It should be a Tennessee there. Something got removed. There we go. TN. So Arkansas, Tennessee, Georgia, Florida, Alabama, Mississippi, and Louisiana. What do we got to do? Well, we have to figure out how many odd vertices there are. And so let's take out a different color and label any that I see that are odd. So Tennessee, that has 4. This one would be even. So we got 1, 2, 3, 4 edges here. Georgia, there's 1. This is odd right here. It's an odd vertex because it has 3 edges coming out of it. Florida, that's even. Got 2. Alabama, 1, 2, 3, 4. If I go around in a circle. Mississippi, 4. Louisiana, 2. And Arkansas, well, nice. It's got 1, 2, 3. So that would be odd as well. And so what theorem, or what part of the theorem applies to that? If you have exactly 2 odd vertices, you have at least 1 Euler path, but no Euler circuit. So I could start, I have to start and end at the other odd. Start at one odd vertex and end at the other odd vertex. Hello again, bell. This makes you feel like you're at school again, right? If you hear the bell and you're doing this outside of school time. I know you want to be at school again. Sure, of course, Mr. Wagner. I live to be at school. No. Hopefully you like school. Hopefully it's not a place you dread coming to. And hopefully I'm doing my part to make it a place where you don't mind coming to. But there are exactly 2 odd vertices. We saw them here. We counted them up. It was just Arkansas and Georgia. So just those 2. So by part 2 of Euler's theorem, there is at least 1 Euler path. Nice. But there's no Euler circuit, just to make a note of that, but no Euler circuits. Okay, but no Euler circuit, and just giving you a little extra information here since it's helpful to have in your notes, since it must start at, not and, at an odd vertex and finish at the other odd vertex. One possible path, or one possible Euler path, I should say, be a little more specific there. One possible Euler path is, well, let's see, why don't we start at Georgia? And so I'm going to, the book, it does something that if we had this copy and paste ability, it would be easy to do, but I don't want you to have to draw these pictures over 6, 7, 8 times. maybe not quite that many times with all of them, but I don't want you to have to draw the picture over and over and over again. So I'm going to show you a way to do this where you could just draw stuff on the picture and I would know exactly what you're talking about. So we're going to use this method to trace out our path when we're doing questions in this class. This will be totally fine for me. So if we start at Georgia, let's say there's going to be more than one possibility actually, but there's at least one. Let's say we started going this way first. Starting here at Georgia, starting at an odd vertex, going to Florida. Let's label that with a little 1. That's just going to say that's our first edge that we chose. From Florida, you would have to go to Alabama. Unless you retrace over an edge you already did, which you can't do with Euler paths, you'd have to go there. So 2, and then I'm just going to continue going around the outside. 3, 4. What the book does is kind of erases these as you go. So if you see a little arrow on it, you can't go over that one again. Think of that one being gone. It's not an option anymore. This would be 5. I'm going to have to end here, but I'm going here. I'm going to say now I'm going to keep going around the outside. 6, so I need to end there. So as I'm looping around here, I'm going around the outside. This is one possible way to do this. Oh, why don't I keep going around the outside there? So I went to here. Now I can't go back this way because I already went over that way, but I can go this way still. So I've got 8, and then I've got 9 going back this way to Tennessee. I've already done this one, I've already done this one, so I have to go this way. This would be 10, and then this would be number 11. I've got an arrow on every single edge. That means I crossed over every edge. I crossed over every common state border, and I ended up back at Arkansas. So what does this look like? This, if you were to draw out the path or write out the path, it would be Georgia, Florida, Alabama. I'm just following the numbers. 1, 2 to 3 would be Mississippi, and then Louisiana, Arkansas. Number 6 was Tennessee. Number 7 back to Georgia. 8 was to Alabama. 9 back to Tennessee. 10 to Mississippi, and 11 to Arkansas. So that would be a possible Euler path for example 2. And before I move on to the next question, I was going to say that you might actually find it helpful to highlight over stuff, but if you do highlight, consider that you cannot erase a highlighter, so be careful with that. But this is just to show you. You don't have to draw the highlighted part in here, but just to show you the path that we took. That was there to there to there, then 4, 5, 6. This is not the only path, remember. There's other paths. Often there will be more than one path, but 9 to 10 to 11. So we just followed the orders there. Notice I went over every single edge. It wasn't an Euler circuit because I started at Georgia and ended in Arkansas, but it was an Euler path because I went over every single edge exactly once. I didn't trace or retrace my steps anywhere. And so that just basically means you could take a road trip. You could start in Georgia, cross over each state border, get a picture at each border. We could start here, go here, and then you could drive to Alabama, to Mississippi, to Louisiana, to Arkansas, to Tennessee, and then back into Georgia to Alabama, cross over into Tennessee, and then drive over into Mississippi, and finally cross over that border. So that crosses over every common border exactly once. Each edge here is represented by the common borders. Alright, so let's move on to Fleury's algorithm. So Fleury, I know the name right here based on, it's a goalie, I think he currently plays for the Penguins. I'm not a huge hockey fan, but I enjoy watching hockey sometimes. And so the Penguins, they've got Sidney Crosby right now. They're a pretty solid team. Not like the Blackhawks. They got a huge streak going. They're looking really good. But Fleury's algorithm, this is not named after the hockey player. This is named after some other mathematician. I tried to find a picture of the guy that this was named after, but no luck. So I just decided to put the guy from the Penguins instead. Okay, so I'm going to make a couple of notes here. The whole thing, I don't feel like we really need to write out the whole thing. I think it's fairly intuitive, but if you wanted to write the whole process down, you could. So you would say, or I would say, see page 841 for the, you could call it the unabridged version, or the entire process. We will practice the process. You can write it down if you want. So write down, if you so desire. If desired, you could write it down. But I'm just going to highlight the two main things. I think what it does for you. It gives you a procedure to always find an Euler circuit, if that's possible, or Euler path. So I'll put Euler circuit / path when it's possible. But we've already said the things in Euler's theorem here that we really need to know. So if it's an odd or no odd vertices, you can start anywhere. If it has exactly 2, you have to start at one odd vertex, end at the other. If it's more than 2 odd vertices, there's no use in even checking. It's not possible. But I think the least intuitive thing, or the most important thing to not do, it's important to, biggest thing that you don't want to do, because then you won't be able to complete the path or complete the circuit. It's important not to choose an edge that is a bridge. And the bridge, remember, it's not in graph theory, it's not necessarily a thing it isn't a thing you cross over water on. It's not that. It's just something that would make it a disconnected graph if you removed it. So do not choose an edge that is a bridge if at all possible. That's the biggest thing to remember as you go through this. So I'll put a little exclamation point there. Very, very important to be doing that. So I want to do one more example with you. And neighborhoods, you could represent them with vertices. This could be a vertex. Wherever you have an intersection of a street, that could be a vertex. You don't have to draw what I'm drawing here. I'm just trying to represent, and then represent with a graph what that would look like. So you could have, this would be like, I was going to say a loop, but it's not a loop. It would be something like that, connecting this intersection to that intersection. You could take this road, this to this. You could take that road right there. Stuff like this. We could go from here to here. This might be a loop, because you're kind of looping back on itself there, and so on. So this could connect over to here, and so forth. So neighborhoods, you could represent those with graphs from graph theory. And so let's say the graph below, it's not going to represent this specific neighborhood, but it's going to just represent some neighborhood. The graph below represents a neighborhood. Perhaps it's Mr. Rogers' neighborhood. I don't know. Did you watch that show growing up? Are you too young for that? Were you around? I was around. I was growing up. He was around. It's a good guy right there, Mr. Rogers. So, is it possible to start at one intersection, which would be a vertex? We saw that here in our little graph, the aerial view of the neighborhood right there. Start at one intersection or vertex and walk each street. The street would be an edge connecting the vertices, connecting the intersections, exactly once. And return to the intersection you started at. Meaning, since you have to start and end at the same place and cross each edge exactly once, that would have to be an Euler circuit and not an Euler path. So Euler circuit Euler path has to be more specific, has to be a special kind of Euler path, which would be an Euler circuit. So it has to start and end at the same place. If this is going to be possible, based on part 1, excuse me, you have to have an Euler circuit, you have to have no odd vertices. So basically, if you see one or more odd vertices in the graph I'm about to draw, it is not going to be possible. So let's see what we got here. So I want you to draw a couple of rectangles like this, and we'll have kind of this diamond shaped in between. There's another rectangle, and I'm going to have a couple of loops, a couple of small circles here and right here. And I want you to draw in vertices wherever you see them on my drawing here. Okay, so there's all the vertices. Now we have to figure out, are any of these vertices odd? If they are, it's not possible to draw an Euler circuit. If there's no odd vertices though, then we're good to go. And so let's give these points some labels as well. We'll just call them A, B, sorry, I meant to call this one C. There's D and E. The one with the loop will be F. Here's G, H, and I. This will be J, K, L, M, and N. I was almost going to say JKL semicolon, because that's what's on a keyboard. Why is that? Why is it that only J, K, and L are the alphabetical ones that go in a string of 3? None of them are alphabetical. What's the origins of the QWERTY keyboard? Okay, back on track. You can figure that out if you want to. But what's my solution here? How many odd vertices, first of all? So count them up. This one, it's even. There's 2 edges out of there. This one, remember, a loop counts as 2. So we've got 1, 2, 3, 4. So make a little circle around the vertex. Count how many edges you see coming out of there. I see 4. Even though this counts as 1 edge, when we're talking about the total number of edges in the picture, it counts as 2 when we're talking about how many or what degree this vertex is. So this one has 2. 2 looks like 1, 2, 3, 4 here. We've got 2 here and 2 here. 3 and 4. That's 4 here. Even. This one's even. This one's even. They're all even. Huh. Okay. Nice. So there are no odd vertices. So let's look and see what we got. Does that satisfy what I needed here? Yes, that was part 1. There's at least one Euler circuit then, and you can start at any vertex and end up getting an Euler circuit. And so let's pick one. But let's finish our thought here first. So it's possible and I forgot to write up here with this question, if so, determine a possible circuit. Sorry about that. So it's possible by part 1 of Euler's theorem. Thanks, Euler. Nice theorem. Good job. Very, very easy to use. I appreciate the theorem. And a possible Euler, he's a genius. That man did a lot for math. He was a brilliant, brilliant man. Okay, so let's say, let's get out a different color at this point, and let's draw in a possible circuit. So I can start and end at any vertex because they're all even. Let's say I start here at I. So I'm going to circle I. I'm going to say this is where I am starting. And it's going to be also where I'm ending if this is going to be a circuit. So it has to be a circuit. You got to start and end at the same place. So let's make a little note of that. Let's point to that here and here. Start and end at the same place. So I start at I could do my loop first. So why don't I do that here? I'm going to say I went in this direction. So I started here, looped around, went back to there. This could be like your cul-de-sac. So you'd have to loop back around like that. We're going to say that's covering the edge only once. And so from there, that's going to be, we'll put a little 1 next to that. And let's say, so I looped around here, and then I just started working my way this way. So I'm going to say that this is 2, this is 3, this is 4. Doing this in a different color. On your classwork, homework, you can do this in the normal color, but let's make it stand out a little better here. Let's call this 6. I'm just going to keep on going along the outside as much as possible to make things a little easier, I think. There are other ways we could draw this Euler circuit. I could start it at any vertex, but this here, now going back to what I had said back here, if you have something that is a bridge, you're not going to choose that edge if at all possible. So right here, I have a choice to make at F. I could either choose to go this way, or I could choose to make the loop. But if I went this way, that would be a bridge connecting this part to this little loop right here. And so if I went this way, I no longer have a circuit because I forgot this part right here. So I have to choose an edge that's not a bridge whenever possible. And so let's say I did that and then I went this way. So I chose the edge that was not a bridge. So that's going to be 10 right there. And now I got rid of that. Now this is no longer a bridge because everything else has been taken care of there. So I'm going this way now. This is 11. This way would be 12. This way would be 13. Okay, I've already went this way. I've already covered that edge. So any edge with a red arrow on it is no longer in play. This one's gone. Now this one's gone. That's 15. This one I already went this way. So I just need to go back around to where I started. 17 and, and 18. And so, we made it. We walked the whole neighborhood. We only walked each edge, each street exactly once, and we went back to where we started. And this is what that looked like. So we have to write this out. You started at I, and then you looped back to I, so it would look like I, and then I again. And then number 2, we went to N, then to M. Just keep going around in the order you see there. So to H, then L, then G, then K, then J, and then F, and back to F. We made the loop right there, back to F, and then to A, B, G, C, back to H, then to D, to E, and then finally back to I where we started. So this would be how we would write our Euler circuit. And there's 6 more examples in the book, remember? You can look at those for some extra help. Don't forget about those. Please utilize those as well as what you've seen here. I think that should do it. The next lesson, 14.3, we're going to talk about something called Hamilton paths and Hamilton circuits and how that's different from an Euler path in an Euler circuit. I think Hamilton paths and circuits actually have more real-life application than these do, but these definitely have real-life applications as well that we've seen a few of them here. Okay, so let me know in class if you have any questions. Hopefully you found that helpful, and hopefully you'll be able to knock the homework, the classwork out of the park. All right, see you guys.